Comparing capacitor discharge and radioactive decay. In capacitor discharge, the charge stored reduces over time with exponential decay. In radioactive decay, the number of unstable nuclei reduces over time, also with exponential decay. We can compare the two processes. Capacitors store charge, which we give the symbol Q, whereas in radioactive decay we have a number of unstable nuclei, which we give the symbol N. The activity of a radioactive sample is the number of decays per second, or the rate of change of unstable nuclei with time. This is given by minus the decay constant lambda multiplied by the number of unstable nuclei remaining. The equivalent in a capacitor would be the rate of flow of charge, or the current, which is given by the change in charge over time, which we can denote by minus the charge over the time constant Rc. The charge remaining on a capacitor after time t is given by Q is equal to Q0, the initial charge, times e to the minus t over Rc. The equivalent equation for radioactive decay would be for the number of nuclei remaining, and this is n equals n0 e to the minus lambda t. We can see from these equations, which are both given on the datasheet, that minus 1 over Rc is taking the place of minus lambda here. The decay constant for radioactive decay is given that symbol lambda, and so the equivalent for a capacitor will be 1 over Rc, which I'll write here. The half-life for radioactive decay is given by the natural log of 2 divided by the decay constant. And for capacitors we don't normally talk of the half-life, but we can when comparing them with radioactive decay, and in this case the half-life is Rc ln2. We'll look into why this is so in a moment. Okay, let's look at the half-life of a capacitor. Well, in general we use half-life for radioactive substances, this being the time for half the unstable nuclei to decay, and we use the time constant for capacitors. This is the time taken for the charge stored to drop to 1 over e, or roughly a third, of its initial value. Sometimes exam questions will compare capacitors and radioactivity, and they might therefore ask for the half-life of a capacitor. This is the time taken for the charge stored to drop to half of its initial value. So starting with the equation Q equals Q0 e to the minus t over Rc, at the half-life, Q over Q0 will equal a half. So we can write that a half is equal to e to the minus t over Rc. If we now invert both sides, the inverse of a half is 2, and in this case the inverse will simply lose this minus sign. So we get 2 is equal to e to the t over Rc. If we now take natural logs of both sides, we get the natural log of 2 is equal to natural log of e to the t over Rc. But the log of e to the power is simply the power, and so we get the natural log of 2 is equal to t over Rc, and so at half-life the half-life t is equal to Rc ln2.